Okay, so let's see kind of how or what we're doing here first. So what we've got is, or what we're trying to do here is we've got a function perhaps defined on two or some interval. Let's just do the same thing that we had done sort of right away with this when we were trying to do area between two curves. Divide it up. I mean, we know kind of what we're going to do here. We're going to be dividing this up into some number of subintervals. And now the goal is to figure out how long that curve is, that bit of curve defined between these two x values. Okay, so we've got maybe one endpoint A, the other endpoint B, and our goal is to figure out how long this function is. Like if you were to pick it up from those two endpoints, lay it out like if it was a string, lay it out flat, put it up against a ruler, see how long that length of that arc is. Okay, so that's the goal here. Okay, so how are we going to do that? So again, we kind of get the picture of how this is going to work, at least dividing it up, but how is it going to work after that? So same sort of idea about finding the area under a curve. We pick some value on each interval and plug it into the function, and that gives us some sort of output value for the function. And then what we had done before for finding areas under curves is we sort of made rectangles. Here what we're going to do is just connect each of these endpoint, or each of these little points here with a straight line, a line segment. Okay, something like that. And then what our goal here would be to figure out what is the length of each of those little line segments, and then add them all up, and then that's going to give us an approximation to the total length of the curve. And then you could probably see where we go with that, but we take the limit as the delta x, the width of each of these intervals goes to 0, and that gives us a better and better approximation. And so again, using straight line segments here is the reason this kind of works, because we can figure out what the length of a line segment is fairly easily. Okay, so in fact, let's just look at one of these line segments here and say, how would I figure out what the length of that line segment is? Okay, so let's just draw it. There's the line segment. And so we're zooming in on this. In fact, let me just make it even a little bit bigger than this so that we can get a better picture of what it's going to look like here. So we're kind of zooming in on just that one little segment there to see how it's going to work. In fact, I'm going to call this x sub I here, just to make it kind of a general x value, so it could just be any of these little subintervals. So I think it's x sub I minus 1 and x sub I, yeah. So if we were to like label these points right here, we would call this one x sub I minus 1, and then f of x sub I minus 1. And that would be what that point is. And then this one would be x sub I, f of x sub I. Okay, now what we need to do is figure out what the length of that line segment is. Okay, so what is the length of a line segment? How do we find that? What formula should we use to do that? And maybe I use different wording here. I want to really find the distance between one of those points and the other one, right? That's really all I'm doing, finding the distance between one point and another. Well, using the word distance, maybe you think distance formula. That's what we're really after here. In fact, we can label this thing that we're trying to figure out. We'll call it L sub I, or length, the length of that little line segment. Okay? And so what is L sub I? Well, distance formula tells us it's got to be the square root. Remember what the distance formula says. Y2 minus y1, or x2 minus x1 squared, y2 minus y1 squared. So what we'll have is x sub I minus x sub I minus 1 squared. That's the difference in the x values, plus the y distance as well. And remember that this f of x sub I could f of x sub I minus 1 could also be called y sub I minus 1 if you wanted to call it that. Same here, you call this y sub I. So I'm just going to do that and say y sub I minus y sub I minus 1. We square that. So that is coming directly from the distance formula. Now, I'm just going to show this sort of, I think it's probably a little bit of an easier way to understand it than what the book does. The book actually does both ways, but I think this one is a little bit easier to understand. Another way that we can label this is the change in x, right? This is delta x squared, right? And that's basically just that. And then the other one, we could call that the change in y, and then square that. Okay. All right, so now what we're going to do next is factor out a delta x. Okay, I'm going to factor out a delta x squared. Delta x squared from under the radical. Now, why would I do that? Well, what's that going to leave us with? It's going to leave us with 1 plus, now when I take a delta x away from that other one, I'm going to have to divide by that, right? Everybody okay? And then just see, that when you distribute that back in there, you do get the delta x squared plus the delta y squared. Okay, so now that can then be rewritten a little bit better. We can write this as delta x squared times 1 plus, let's just call this 1 plus delta y over delta x quantity squared. Okay, now notice then you can take that delta x out of there since it's squared. So really what you can rewrite this as 1 plus delta y over delta x squared, and then you can put that delta x here at the end. Okay, so this is squared, and we took the square root of it. That's why we can just take that delta x and stick it on the end there, take it out of the radical. Okay, now what we need to realize here is that's going to give us the length of one of those little line segments. And then what we could do is figure out to find the length of all of them added together. We would then add these all up. And in fact, actually, this probably should be called delta x sub I, delta y sub I. So then to get an approximation of the total length here, we could add all these up. Okay, and then we can take a limit of that to get the exact area, the exact length of the curve. So the exact length of the curve is going to be this, the limit as in this infinity of all of this stuff. Okay, now when we take a limit of this thing, in particular, what we need to notice is that when you take a limit as n goes, or really it's also as delta x goes to 0, n going to infinity and delta x going to 0 basically do the same thing, right? Because delta x is the width of each subinterval. If you let that shrink down, then by definition you have to have more rectangles. So basically, you can say this in two ways. You could say the limit as n goes to infinity, or you could say the limit as delta x goes to 0. But if you do it this way with this particular definition, that actually looks an awful lot like the definition of the derivative, and in fact that's exactly what it is. And when you take this limit, when you let that delta x go to 0, what happens is that those deltas turn into d's, and what you get is this, right? That is the derivative, dy dx. Okay, so those become differential quantities. So what does that mean? That means that we can rewrite this formula for the exact length, and the rest of that is pretty much exactly what we've seen as to define a definite integral, and so that's exactly what this is. This becomes a definite integral with that delta y over delta x becoming the derivative. So what we get is 1 plus dy dx squared, and then the delta x on the outside also turns into a dx. And so this is the formula for the arc length. This is the arc length formula right here. There's another way to derive this formula. It's a little more complicated. It takes it's a little bit more involved. So if you want to see how that one works, the book goes through it. It actually requires the mean value theorem for derivatives to prove it. So I don't really want to go through it because it is a bit confusing. So this one I think is maybe a little bit more intuitive to see kind of how we're getting this formula. Okay, so there it is. That's the formula for the arc length. Now, what you can kind of notice about this formula is that it's kind of complicated. Like if you want to find the arc length of a function, what does it require that you do? A function on an interval. You have to find the derivative of that function, right? That's what this is saying. You have to find the derivative of that function. Then you have to square it, and then you have to add 1 to it. And then you have to take the square root of it, right? That can lead to some pretty complicated stuff, right? Especially if the derivative happens to be kind of complicated. And then after you've done all that, then you have to integrate it as well. So this is definitely it's not a really nice formula to use. And in fact, most of the time, it's pretty hard to find a function where you can actually do all that to the function and expect to get an integral that is like doable, right? And so what you see in this particular section is that the authors of this book have found pretty much all of the functions, or a lot of them, that when you do all this stuff to the function, that then you get an integral that you can actually do by elementary methods. So let's take a look at one of them to see kind of how this actually works, and we'll see that this formula is not particularly nice. Although sometimes it can be if they pick a good function for it, as they do in this first problem. It actually turns out to be pretty nice. But you can imagine, like, why did they have to pick the natural log of the secant function to make this work? Well, we'll see in a second why this particular function actually works pretty well with that formula. So they give us a function, they give us an interval, and this is the way it's always going to work on these. They'll give you a function, they'll give you an interval, they'll say how long is this, or find the arc length of this function on that interval, okay? All right, so let's just go through step by step here. The first step is we have to find the derivative of that function, whether we call it f prime or dy dx, it doesn't matter. Just find the derivative, right? So what's the derivative of the natural log of something? So we've got to kind of remember that too. What is the derivative of ln u with respect to x? Remember that one? Yeah, 1 over u prime over u, exactly. U prime over u, that's the derivative of a logarithmic function, or the logarithm of a function. So in this case, u prime, well, u in this case is secant, so u prime is the derivative of secant, which is secant tangent. And then divided by u, which is just secant, right? So you can kind of see why they chose this particular function, because the derivative actually ends up being kind of easy, just tangent. And so then what we're looking for, now we need to plug this into the formula. So arc length should be the integral from 0 to pi over 2, or pi over 4, I mean, of the square root of 1 plus the derivative squared, right? And the derivative is tan x, so the squaring that, you get tan squared x. And again, you can maybe see why they chose this particular function here. Because what's that? What is 1 plus tan squared? Secant squared, exactly. So that means that this then becomes the square root of secant squared by a Pythagorean identity. And so all we just get there is just secant x, right? Square root of secant squared x, just secant. Okay, so we end up with, after this formula, we end up with the integral of the secant function. And we hopefully remember what that is. That's the natural log of the secant function plus the tangent function. And then we have to plug in our bounds, subtract. So let's see, if we plug in pi over 4, we get the secant of pi over 4. I'm not going to bother with the absolute values here because they're positive anyway. What is the secant of pi over 4? Remember that? Yeah. So what's the cosine of pi over 4 then? Okay, so we should, at this point in Calculus 2, if I ask you what the secant of pi over 4 is, you guys should all know that. Yeah, root 2. Root 2. Because this cosine of pi over 4 is root 2 over 2. You flip that over, you get 2 over root 2. Well, that's the same as root 2. And then what is the tangent of pi over 4? 1, exactly. Tangent of pi over 4 is 1. Okay, good. And then don't, in this particular case, we also probably should at least think about what happens when we plug in 0, because we're dealing with trig functions. So if we did plug in 0, we would get the secant of 0. Well, the secant of 0 is actually 1, and the tangent of 0 is 0. So what we end up with there is the natural log of 1. The natural log of 1 is 0, so in fact it does just disappear. That next term is just going to be 0. So that's it. The length of our arc length on this function, on this interval, in other words, if we were to graph this function on that interval from 0 to pi over 4, and somehow we're able to chop off the ends and just lay that function out flat and measure it, you would find that its length is ln root 2 plus 1, or whatever the decimal approximation of that is. Okay, kind of, is that clear what we're doing? Finding arc length. One other thing that we have to be aware of on this type of question is that we could define the function differently, right? If x equals f of y or g of y, so if x equals g of y, well, if that's the case, then that whole process that I just did to derive this formula, remember that one step where I factored out the dx, or the delta x? Well, I could have factored out the delta y just as easily. And if I had done that, then my derivative would have been dx dy. Okay, so dx dy is basically x prime of y instead of y prime of x. So the formula ends up being almost identical if you have a function defined in that way. You can see it at the top there, right? It says for a smooth curve given by g of x equals g of y, the arc length is, and then it's basically the identical formula, except instead of dy dx, it's dx dy. And then also at the very end, you've got a dy instead of a dx. So all that's saying is that if you have a function defined in this way, you just have to take the derivative of dx dy, and you have to integrate with respect to y instead of with respect to x. So that's the difference. So that's in fact exactly what's happening in example 2 here. We've got a function defined in that exact way, x equals f of y. So now we want to find the arc length of this function on this interval from 1 to 4. So again, the only difference here is now I'm going to be finding dx dy instead of dy dx. And then I integrate with respect to y. So dx dy in this case, just normal derivative, multiply the 3/2 by the 2/3, I'm just going to get 1. So I get y minus 1, and then I lower that by 1, I get 1/2 power. Chain rule doesn't really apply here because I've got the derivative of y is just 1, so that's it. There's our derivative. Okay, so then I want to plug that into the formula. We'll get what is the square root here? What is the square root of y squared? So here we've got y minus 1 to the 1/2. That's dx dy, and then we want to square that. So that's kind of nice because you could see what happens there. That's just going to give us 1 plus y minus 1, right? Which is just root y. So again, you can maybe see why they're choosing these particular functions for us to find arc lengths for, because plugging all this stuff into that formula actually ends up giving us a function that's pretty easily integrable, right? Okay, so then the arc length here is going to be integral from 1 to 4 of, we've done all that we need to do there, 1 plus dx dy squared, square root the whole thing. We ended up with this, right? Just root y. So that is the integral that we have to find here. Again, a pretty simple one to do. Write it as a power function. Raise that by 1, so it's going to be a 3/2, so we'll need a 2/3 y to the 3/2. Plug in 1 and 4 and see what we get. If I plug in 4 there, I'm going to get 2/3 let's see, 4 to the 3, that's the square root of 4 is 2 to the third power is 8, so I'm going to get an 8 there. And then minus, plugging in 1, I just get 2/3. So that's 16/3 minus 2/3, that's 14/3. So the length of this particular function, x equals 2/3 y minus 1 to the 3/2, on this interval from 1 to 4. Again, if you were to somehow able to cut that bit of function out on that interval, lay it down flat, measure it, you would find that its length is 14/3, whatever units you're using. Okay, so let's try a, oh yeah, that stuff about the arc length function, I'm going to skip that because honestly, this is the first time, well, I taught this class quite a bit at UTEP before I came to CNM, and in the book that we used there, they didn't even mention this thing about the arc length function. It just wasn't part of the book at all. So, you know, one book doesn't even think it's important enough to put it in there. This book, for whatever reason, puts it in there. I just don't think it's really that important, so I'm just going to skip it. Although I will just tell you kind of what it is saying, what it's doing for us here. So they tell us the arc length function is this. So what does this function actually do for us? And I'll try to maybe draw a picture of what it's doing for us. It said it's a function of x, right? So you can kind of see it's s of x. That means that the variable in this function is x, and so where the x actually shows up, it's at the top bound of the integral. And so how do we actually even interpret what that function is telling us? Well, it works kind of like this. You would start at some x value, a, and then you have a function that sort of, you know, goes off doing whatever it's going to do. The function we'll call f of x. What this arc length formula is allowing us to do is basically telling us what is the length of this function as a function of x. In other words, suppose I wanted to figure out what the arc length was out to this number right here called x. What that function is going to do, in fact, let me call it, I don't know, it doesn't even matter. Let's say it's 10, right? So I want to figure out the distance from that a value to out to 10. Then what I would do is I'd plug 10 in as the upper bound here. And so what I would find is that it would tell me the length from here up to that number 10. And then that would be the length of that bit of the function, you see? And then I could change that, right? Because x is the variable, right? So I could then say, well, what's the arc length if I go out to, I don't know, 15 or something like that? And then if I just plug 15 in to here, then I would spit out some number, right? And then that would actually just extend the length of the arc out to there. In other words, what it's doing for us is saying, if I have a starting value, a, whatever that is, it's a fixed value, and suppose I want to figure out what is the arc length out to 50. All I got to do is just plug 50 into the function, and it'll tell me what the length of that arc is all the way out to 50. If I want to know what the length is out to 100, I just plug in 100. It'll plug it into that formula. It'll tell me what the length of the arc is at that, from a to 100 or whatever value I plug in. So it's telling us the length of the arc for any value of x, starting at some fixed value. Okay. Again, I'm not really sure what use that really is to know that, and I'll tell you the functions that usually come out of that are extremely complicated. So I'm just not even going to do it. But anyway, that's what it is. I removed all the homework about that from this section anyway. So really that's it as far as arc length. That's it. We've done a couple of examples. The examples that we've done are actually not even that bad. So, however, I will warn you that number 2 there, problem 2 that I want you guys to work on is pretty tricky. That one is a pain. Problem 1, I don't think that one's particularly difficult. Definitely not as hard as problem 2. And then problem 3 is the arc length function question. So again, we can skip that one. So for now, just go ahead and do problems 1 and 2. I'll give you a few minutes to do that. Michael, do you have those worked out already?
Oh yeah, I got them on here.
Okay, cool. So go ahead and try to do those couple problems, and then Michael, you can pop them on the board and just see how. Again, before you maybe look at Michael's work on there, just try to do it yourself. So that first one, again, you'll take the derivative dy dx, you'll square it, add 1 to it, take the square root of that. and then see if you can figure out what the integral is. And then on problem 2, that one again, that's pretty tricky. Probably will need help on that, but see if you can figure it out anyway. So I'll give you a few minutes to work on those, and then we'll come back and go through them. Okay, let's go ahead and go through these problems. All right, so that first one, derivative, not too bad, 9 root x. Square that, you get 81x, and then add 1 to it, right? That's what's going on right here. So that's just taking the derivative, squaring it, and plugging it into that formula, root 1 plus derivative squared. So at that point, this is a substitution integral. So you can see the substitution that he did over here. U equals 1 plus 81x. The derivative of that is 81. You have to divide both sides by that 81 to get rid of it. And then you've got this. That's where the 81 went. And then don't forget to change the bounds, right? So the bottom bound was a 0, right? It changed to a 1 because why? We plugged it into the substitution right there. If you plug in 0 there, you get 1. The top bound was 1. If you plug in 1 there, you get 82. And so that's the new top bound in the U integral. Okay? Antiderivative, that's this. And then multiplied by the 1 over 81. Multiply it out, plug in the 81. Oh, 82, I mean, plug in the 82. Plug in the 1, take the difference, and you should get something like that, or whatever the decimal approximation would be. So that one, not too bad, comparatively speaking, compared to some of these other ones. So the second one on here is the difficult one. That's the, why is it difficult? Well, you can see the derivative here. There it is. That's the derivative. That's just power rule, or I'm sorry, that's just rewriting the function with power functions, and then take the derivative. We get this one here, and then simplified over there. So that's the derivative. All right, so then with that, notice, well, when you square that thing, you get this, right? Squaring that gets all this. And then adding 1 to it, notice what adding 1 is actually going to do here. You get that minus 1/2 right there. But when you add 1 to that, it's going to become a plus 1/2, right? Plus 1/2. So now at that point, he factors out the 1/4. That leaves that with a 2 right there. And you can verify that if you distribute that 1/4 back in there, you will indeed be left with the 1/2. Now at this point, this part between here and here is kind of the tricky part here. You have to realize that that thing is a perfect square trinomial. In fact, I think I might just go through this problem one more time just to show kind of that series of steps there is pretty important, because we're going to kind of see that happening over and over again. So I might just go through and clarify that a little bit more, because that step right there is maybe not entirely clear why that happens the way it happens. Okay.
One thing you can do to verify that step there is to start at the arrow where we have y cubed plus y to the -3, and that quantity is squared. If you FOIL that out, then you'll end up with the previous parenthesis.
Yeah, let me just go ahead and go through that bit again, because I do that part a little bit differently than Michael did. But after that, I mean, once you finish that part there and square it, and then, or once you do all that and then take the square root of it, if you can see here, this piece that you actually end up with is a perfect square, right? There's a second power on it. So when you take that square root, that's what makes this problem actually doable, because you do end up with, this right here, which is actually not that bad. But getting to that point is the hard part. So I'm just going to go ahead and go through that again. It's a little bit of a different take on it, I think. Okay, so we found that the derivative dy dx was 1/2 y to the third minus 1/2 y to the minus third. And when you add 1 to that, or actually when you square it, let's go ahead and square it, dy dx squared. I'm just going to put the 1 plus there as well. So if you square that thing, just remember you have to FOIL it out, right? So you're going to get this. And I want to do this problem in detail again, just because it's fairly common what is going to happen in this problem. We're probably going to see it at least 3 or 4 more times in different problems that are kind of like this, both in this section and in the one with surface area. Okay, so try to follow along with what's happening here. So again, squaring that thing, we're going to get 1/4. In fact, actually, I don't think any parentheses on that. We get 1/4 y to the 6th, and then let's see, this outer terms are going to be another 1/4 and another. So just notice what happens on the outer terms here when you FOIL this thing, like this one times this one. What's going to happen when you do that? And in fact, also on the inner terms, right? This one times this one. You see what happens there? The third power and the minus third power, what happens there? Well, those cancel, don't they? Because when you have a minus 3 power and a plus 3 power, you get the 0 power, and that's just a constant. So you're going to get the 1/4, 1/2 times 1/2 is 1/4. You're going to get another one of those from the inner functions, right? FOIL, right? So the outer gives you a minus 1/4. The inner also gives you another minus 1/4. So that actually ends up being a minus 1/2 there. And then finally, the last terms are going to get you this 1/4 y to the minus 6 power, and then this plus 1 is just sort of tacked onto the end there, right? That's from here, just what's under the radical. And again, what that does, the plus 1 and the minus 1/2 change this to then be 1/4 y to the 6th plus 1/2, and then plus 1/4 y to the minus 6th. Okay, so everybody okay with what we've done so far? We've just taken the derivative and we've squared it and we've added 1 to it. Okay, the next thing we would actually want to do would be to take the square root of it. But before we take the square root of it, we want to get it into that form that Michael was showing us, where it is something squared. Now to do that, I think this, for me anyway, this is probably the best way to kind of see what's happening with that thing. I'm going to just go ahead and write it all out like this. And with positive exponents. Okay, so y to the 6th like this. Okay, everybody okay with that? I just moved that y to the minus 6 down to the denominator. Now what we want to do here, if you have a really sharp eye, you could probably notice that this thing here is itself a perfect square trinomial, but it's kind of harder to see that since we've got these fractions and stuff in there. So what I suggest is at this point to multiply through by the LCD, add these all together as fractions. The LCD is this right here, 4y to the 6th power. So to get the LCD everywhere else, what do I need? Well, in this one, I need a 2y to the 6th, right? So on the numerator and the denominator, 2y to the 6th. That's going to get me the 4y to the 6th. This one, I need a y to the 6th, right? So I multiply by y to the 6th in the top and the bottom. Okay, so that's going to get me the LCD. I'm going to end up with y to the 12th power plus 2y to the 6th power plus 1. And in the denominator, since we have the LCD, we can just put it all over that LCD there. Okay, so there we go. Now at this point, it hopefully is a little bit easier to see that that numerator is in fact a perfect square trinomial. And remember what a perfect square trinomial is. It's where you have this a plus b quantity squared. That always produces the same sort of thing. It produces, a squared plus 2ab plus b squared, right? And so if you look at that, look at what we have in the numerator there, that's in fact exactly what's going on, right? A in this case would be y to the 6th. That's this. That's a squared there. Oops. That. And then, so if a is y to the 6th and b is 1, then that's what you have as the middle term is 2 times a times b, and then this is b squared. So we just have to recognize that that is a perfect square trinomial, and it can be factored as y to the 6th plus 1 squared. That's the whole key behind why this problem works, because again, the next step on this would be to take the square root. And now that it's written like that, everything is a perfect square, right? Y to the 6 plus 1 is a perfect, or squared is a perfect square. 4 is a perfect square. Y to the 6 is a perfect square. All of that is a perfect square. So for that reason, when we get to this particular step, the square root of 1 plus dy dx, in fact, I guess in this case it has to be dx dy, dx dy squared, well, that means we're just taking the square root of this, right? Y to the 6 plus 1 squared over 4y to the 6. And again, we notice that all of that is perfect squares. So this then becomes y to the 6th plus 1 over 2y to the 3rd, which can then be further simplified to be y to the 6th, or let's we can write that as 1/2 y to the 3rd plus 1/2 y to the negative 3rd. And then both of those are power functions. Integral is doable at that point. So basically from there, you would say that the length of the arc is going to be integral from 1 to 2 of that thing that we just did, 1/2 y. In fact, you can even pull the 1/2 out of there if you want to. Well, I guess we don't really have to. Integral of this thing. And then those are just easily done by power rule. Raise that to the 4th power, we're going to get 1/8 y 4th. Let's see, if I raise that to the -2, I'm going to have minus 1/4 y to the -2, right?
Mm-hmm. Yeah.
Plug in the 1 and the 2. And from there, it's just arithmetic. So what did you get for your final answer on that, Michael?
Let me go back and, oops. What was that, number 2? Looks like, oops, that's the wrong problem set. Sorry. 813, got them all in the wrong order. Looks like 33/16.
33/16. Okay, cool. So after you plug in the 2 and you plug in the 1, simplify that, you should get 33/16. Okay, so like I say, just be aware of this situation where simplifying this trinomial, or the trinomial basically, in this particular section and the next one, we're going to see that happening quite a bit, where we have this perfect square trinomial showing up